Hello and welcome to the Entropy webcast. Today I'm joined by Shaheen and Waylin, and we're going to be talking about micromodels. So micromodels has become something that Entropy's become really known for. To be honest, it's I suppose the secret that allows us to go in and deliver intelligence where others have struggled before, and in some of the most complex operational environments. And so we wanted to do a specific webcast dedicated to micromodels. We're going to talk about why an approach such as micromodels is needed, what micromodels is, broadly how it works. We're also going to touch on synthetic data as well. So there's a lot to get through. But before we start, as with all of the webcasts, there's a couple of announcements to make. So the first is that Waylin has been nominated by the University of Essex for the Rising Star Award, which is a very, very good achievement. You've been nominated as a finalist in those awards, so fingers crossed for the ceremony. And Entropy in general has been out and about across multiple conferences over the past month or so, and we've also participated in the recent Logistics UK industry report, AI report, as well as going on to their podcast. So if there's an opportunity to interact with any of those materials, I would recommend doing so. But yeah, as always, it's great to get out and speak to many people operating in this space. But without further ado, let's get into today's topic. So micromodels. Now, Shaheen, we first came up with this sort of together, didn't we? And I think when we talk about why, because we're going to go very problem solution in this webcast, which is a little bit different to how we've done it in the past. But I do think we need to start by articulating why an approach like micromodels is needed before going into talking about what it is. And when I think about why it's needed, I go all the way back to the port that we originally started trying to profile traffic for. Do you remember those days?
Yeah, that's right.
And I thought I'd maybe ask you if you could summarize relatively simply for our audience the overarching problem with traditional modeling approaches and why we had a need to create the micromodels architecture.
Yeah, that's right. The example that you said, the port of Dover, that we started to creating a model for traffic for them. So first thing is the complexity of the problem. So when the problem is too vast, is too many features involved, and for example, in the traffic, there's a big area that you want to cover. So it's going to be very hard for a traditional model to have everything in and be trained on all these data that is gathered through all the area. So, and the accuracy will drop drastically. And we had faced that issue before. So then we started to thinking reversely to see, all right, if we cannot do this all at once, let's do it step by step. Let's do it piece by piece. So instead of creating one model that solves it all, we created a lot of model as much as it needs to have a more accurate, more atomic, and less complex model for each of these small processes that is involved inside the whole model that we're trying to train.
Yeah, no, that's brilliant. Thank you. And I just want to unpack what you said in terms of the process is too complex for one model to do it all as one. I suppose there's multiple threads to that. I remember finding it very, very difficult to get hold of data. So the classic thing you do if you're trying to predict traffic to a location or anything, to be honest, if you're trying to predict any complex operational workflow, you'll sit there with a whiteboard and you'll list all of the data features that you think are relevant to that problem. And then you'll go off and try and get all of those data features. And that's basically what we did. I remember trying to do it at Portsmouth as well. So the first one was the amount of data that you need to get. But then inherently, when you start getting into the weeds, actually, a lot of these problems, a lot of the different parts of the problem are very, very different.
That's right.
Maybe you can explain a little bit more about that.
Yeah, the amount of data is really important because sometimes you have too many data that's training on them doesn't make really much sense because data is very different from each other, and they might not affect each other as we consider them to do. And the other thing is the quality of the data. So for example, if you have one feature, maybe the quality of that specific feature is very high, but the other features that we are taking into account for our model training are not that good enough. So it will affect, and eventually you're gonna have a bad model at the end. So yeah, the amount of data, how to get the data, it's a big
Coming
issue.
from lots of
It's
different
coming
places.
from, yeah,
You're
different
not going to get
sources.
some, you're going to get other bits.
Yeah, exactly. So all in one, it's going to be very hard to create a traditional model in that sense.
And then, Waylin, when you think about a problem like predicting traffic to the Port of Dover, or like trying to predict passenger movement through Glasgow, or like trying to predict, future biogas yield at an AD plant, these are typically made up of lots of independent problems kind of linked together, right? And one of the things that we find, or one of the things I can imagine, is that each one of those problems is quite different in the way that it behaves. I mean, how important is that to recognize from a data science point of view?
I think, sometimes even you are solving the same problems with the different, and you get the data from the same source, the pattern could be different. The data pattern could be different. And in that case, if you treat them as the same problem, it can't work when you're building one model. And so in that case, you need to split into the tiny problems based on the patterns, based on the data's features difference. And for example, like port, we have different vessels coming in. So if we treat all the vessels into the same data set and then build one models, it won't work, because different the big vessels and the small vessels might have the different behavior. And when you treat them into the same thing, they will think, okay, the model cannot recognize that well. They're thinking, wow, this is a 100 meters vessel, and there's a 100-meter vessel for the cargo and a 100-meter vessel from other things. In the model, in from the data, it shows different pattern. But when you push two things into the one model, the model think, sometimes they work like this, sometimes work like that. How the difference between the different data? In that case, we need to split the problems into the smaller one to make sure that, yes, this micro model only focus on this part of the data. And after that, you connect these two together to chain it and then to predict the same problems, like to recognize the different pattern and then go to the model and then chain the model together.
So we'll go deeper into exactly how micro models work in practice, the chaining, the identification and so on. But I just want to stick a little bit more on the problem statement for now. I mean, when you said a really interesting thing there where, even if it's the same problem, you can't treat them as the same problem if they're in different locations, perhaps, because the data is going to behave slightly differently, or there's going to be different feature quality or importance and so on and so forth. Shaheen, question to you. If we were to look at everything as the same, what would happen? Like, what's the result?
Right. As Belin said, the characteristics and the behavior is totally different. Even, for example, predicting the same concept like traffic. So the traffic, for example, down to London is totally different to up north. So if we consider that this is traffic, the features are the same, the concept is the same, everything is the same, but at the end, the model will be entirely different. So if we do the same model for every same concept, this is not going to work. And we had this issue before.
And the result is poor accuracy or overfitting. And basically, for the audience, again, some people that are watching this are not going to be data scientists per se, just in really simplistic terms. What would they see from a model that hasn't necessarily got that level of fidelity? It hasn't got that concentration on the nuances within an environment. I suppose it'd be overfitting. It would basically give the same value all of the time.
Yeah, it can be, many things can go wrong actually. Overfitting, underfitting. It can be very, very low accuracy. It can be wrong predictions. Everything can happen.
Yeah, no, that's really, really helpful. And I remember, when looking at this traffic use case, we ended up with models on specific junctions of a road. So, each junction, we're talking about 3 miles apart, perhaps, completely different behaviors, completely independent models and so on. But if we'd have done it as one model, we wouldn't have got the accuracy that we wanted.
Yeah, exactly. Yeah, the thing is, when you want to actually do these small atomic macromodel pieces, you have to have some kind of knowledge about the whole situation, the whole problem that you're making. Because when we first started to create the traffic model, we didn't have any knowledge about that. Then we started to learn that how it actually works, how the traffic going to build up down there at the port of Dover. So you have to have some knowledge. It's not like just splitting up the task into small pieces and that's it.
Okay, so micromodels is also a way to kind of bake in gradually and iteratively over time domain expertise. Whereas a big model approach, you have to have all of that from the outset. There is no chance to kind of learn as you go. So if I was to summarize the problem, people looking at complex environments like ports, like road networks, like airports, like AD plants or renewable energy, you're trying to predict specific aspects within that operation. There's lots of data, but it's coming from lots of different places. Some data's good quality, some data's bad quality. You don't necessarily have jurisdiction over all of that data, so you're going to have to ask partners to contribute data. And the problem is filled with heterogeneity effectively. So it's every single there's lots of different flavors of the same problem, and there's lots of different types of problem throughout. And so you're sitting there looking at this minefield of complexity, not sure you can get all of this data, not sure that the models are going to be effective, or when you've tried to deploy models, they haven't been particularly effective in the past. And you don't necessarily have all of the domain knowledge, or you don't necessarily know what sort of domain knowledge we need to build into the model from the outset. So for most people, they stop.
That's right.
And for most of these environments, they either fail spectacularly, they deliver something that takes a very, very long time to build, a one model approach, a very, very long time to build. You're waiting to get all of this data before you can do anything, and maybe years. And then you get to the end of a 2-year project and you have got a model that's not performing particularly well. So instead, we came up with micromodels. So now, Shaheen, I know you've touched on this already, but would you be able to summarize for me what micromodels is in the simplest language you can possibly think of?
Yeah, I'll try to. So a micromodel, as we actually define it, is a series of models that are atomic. They're not related to each other. They're working independently with independent features, and they can work separately. So it's not one depending on the other to work. So basically, it's like splitting the whole big complex problem to smaller pieces that are working independently. So each of these micromodels can be different type of models. It can be machine learning, can be other types of machine learning, can be neural networks, anything that can actually solve the problem. It can be
logical sometimes.
It can also be logical, yeah, and can be rule-based, can be like fuzzy models and other stuff. So it doesn't matter the type of the model, it's the concept that they should be independent and they should work separately. And they, at the end, you're going to have to chain them and to get the outcome that you want.
So this network of models that we end up with, when working with micromodels, when working with the methodology, and so you've built many micromodels, together, it's your team that ultimately works on all of this stuff. But when you're working to build a micromodel, give me a sense of how many features are we typically working with? I know it's not a straight rule, but just give people an idea of what sort of scale we're working with in terms of the number of datas.
That's really hard to answer, I think.
Okay, so let's pick an example. Let's pick one of the models on the road. Can we remember how many? Do you know off the top of your head?
Yeah, well, I think the one that we done had probably about 40-50 features involved.
Yeah.
But it's actually very dependent on the type of the question, and you have to have this knowledge that I mentioned. So based on the knowledge, you will understand that what kind of features is going to affect your outcome. So you go look after them and look for them, and you get them from different sources. Then you can come back and see if you need any type of mixed features, if you can have some kind of calculations with your features that you have. So to create more features in. And if you can have more features in, if you have some other factors that haven't been into the operation before. So for example, there are things that maybe the operation in the ground doesn't actually know about. So you will have to look for it. It's very dependent
So
on
it's not a fixed answer.
there is not a fixed
But I
answer.
suppose the point I'm trying to make is we are working at a level of resolution that's quite high.
That's right. Yeah.
And what kind of advantages does that give you from a data science perspective? So when you're trying to build an accurate model that predicts an atomic piece, is there an advantage? Well, clearly there's an advantage, but what are the advantages from your perspective of working with a narrower problem statement? Let's call it that, rather than a narrower feature set.
Because when we are only consider about a narrow questions,
Yeah.
we consider less features. If we consider a general questions, we will need to consider more features in one questions.
Yeah.
And then after that, we need to analyze the different features. It's okay, is this feature is gonna fit into this general questions, or is that feature is gonna generate consider into this questions or not? But when you go to the narrow questions, the features that you need to consider is more related directly to that questions.
Okay.
So in that case, you split the features into facing the different questions. Then it will spend less time for you to select the features. You just okay, this is 10 features is completely relevant to this questions. Another 10 features is completely relevant to the another questions. So we just focus on this 10 features. If it's good enough for these questions, or do we need more features from the other place to fit into these problems? And we don't need to put the same features into the another problems. So it basically spend the time.
Yeah, it takes less time to kind of dig through it, but I can just hear it. The focus that you have, but also because of that focus, the amount of detail you can go into for each individual feature that you're selecting must be a huge advantage in terms of being able to produce accurate models, accurate predictions at an atomic level.
Yeah.
But then, of course, we've got an atomic piece of the problem, a very, very small, distinct prediction that on its own doesn't mean a huge amount. And you've both mentioned to me this concept of chaining. So getting these models to work together. Waylon, perhaps you could explain again in as simplistic terms as you can what we mean by chaining. So we've got lots of these models, maybe we've got 10 of them. What do we mean by chaining?
I think that's more like an engineer part.
Yeah.
It's we have the outcome from each model.
Yeah.
And how to make those outcome works, we use the engineering way to make all the outcomes work together, and then shows the clients about the final results.
Yeah.
So that's what I'm understanding about the chaining.
So and it's really important to make the distinction between science and engineering, data science, data engineering, and it's those two disciplines working together. I've always said, one of the rarest things about micromodels is it's not a pure data science approach, right? Data science is building the algorithms ultimately that produce each one of the predictions. But data engineering is how we then make these things work using ontology, using various other bits and pieces to actually get lots of discrete micro models to actually deliver something useful for the end user. I mean, is there anything you'd add to that data engineering comment?
Well, the whole idea that was basically underlying the chaining the models is the federated learning.
Yeah.
So it's like each of these piece of models have some kind of insight that can provide us. So between each of these insights, something can happen. Something else can affect the overall outcome that we are interested in. So with data engineering, we can implement it as well. For example, in a chain of models, in the network of models for a traffic, we can actually see if an accident happens in between two of these models, how it's going to affect the overall outcome that we are looking for.
And that's because we've got atomic models that have gone through an engineering process. I'm going to replace engineering with ontology because ontology is something that is absolutely foundational to NTP. But the ontology effectively tells us how data relates to one another. But if you take it into this world, it tells us how each model relates to one another, where they are geospatially, where they are temporally, what matters from various different factors, so that when a car incident happens, which is not model derived, that's actual, we've just observed that from another data source. What you're saying is actually we can use these chains to capture that event and understand the impact that that's going to have on the network of models, and we can actually learn how events affect the network of models by looking at inputs and outputs from each and how they relate, and that's the federated learning process.
Yeah, exactly.
Really, really amazing. And the other big benefit of micromodels, and this was something that we saw very early on, which was, so we've spoken about what micromodels is: discrete models, loads of focus, smaller feature sets, better accuracy, chained together. But you can do it iteratively, can't you? You don't have to go all or nothing.
Yeah, exactly. Yeah. And that's actually the way that we work in the process of working with some new customers. So we always start small. We always take one part after the other. So, for example, if you want to work with the Port of Harwich that we started with, we didn't go for we're gonna give you everything at the first. We said we're gonna go small and we go part by part. So we started to understand the different processes that's happening inside the port, and to pick the one that is independent that can be fit into the micromodel strategy that we have.
Sorry to cut you off. I think that's really important, because we come in with with essentially the proposition of a unified intelligence layer. So this is a layer of intelligence. It combines AI, digital twin, machine learning, to create a a continuously updating operational picture of everything. And then we have agents sitting over the top of that, and they're looking for things, and they're identifying problems, and they're communicating them out with operators. And, leaders can go and interact with an episodic agent, a strategic agent, and ask really, really deep and powerful questions. And we show that. And for most people, they feel kind of daunted, because actually they sit there and go, well, we don't have the data to do that. I don't know what order my data's in. I don't know what data is going to be relevant. I don't even know if we can do this at my port. But this ability to go step by step and actually start with a small subset of a problem and not have to build the whole thing at once is so powerful, isn't it?
Yeah.
And we've seen this so many times. But if I was trying to take a big model approach and come in and provide, I don't know, just the more kind of conventional, one shot sort of approach to all of this, you would have to spend time doing data workshops and data exercises. Whereas our start point is we'll build a model here, and then we'll build another model here. And then, Waylin, as we go through that process, do we learn things about what data might be important that we didn't know at the start? So we deploy a model and then we think, actually, this data would be really, really important now.
Yes. I think during the whole process, sorry, at the beginning, because when we consider the questions, it will be just like a general idea about that. So at the beginning, when we're building the models, it will be just like a model with the basic knowledge that we thought we know. But during the time that we talk to the clients, try to improve the models, they will have like a more factors, like a more important features coming in. Okay, we didn't consider about that. And then when we add that in, maybe it will improve the models. Maybe it will make the models like worse. We don't know. But it's like a learning process to make sure that the development of the models get to become better and better. And then in that case, it's the human learning the knowledge and then put that into the model. So it's not just the model learning stuff. I think as a developer, we also learning what's the knowledge to build these models and then to put that part into the model. Yeah.
That makes complete sense. And, how many times have we found data that people have thought is completely irrelevant and we've done something with it?
Yeah. Exactly.
And I just want to go back, because you mentioned Harwich, and this will segue very, very nicely into the next part. But we started small, like you say, and we actually started by trying to predict pilotage movement. So we wanted the pilotage movement duration. And the reason we started there was because it was, we looked at the overarching workflow and we said, look, if these are the various questions that we need to answer, that looks pretty fundamental to about 3 or 4 of them. So if we can't get that, then we're not going to be able to do much. And so it became arguably the hardest of all of the problems that we had to solve. But the thing that made it infinitely harder was data availability. Right. Perhaps you could just expand a little bit on this, because again, I'm thinking about what the audience is going to be listening. They might understand discrete models, break complex problems up, deploy iteratively, chain these models together, integrate real-time data. Sounds great, but I literally have no data.
Yeah, that's the problem that many people have. So, and apart from that, it's actually the cohesion of the data. So some companies may have some different data taken from different data sources, different IoT devices, different metrics, and anything can be different. So they will say that this is one feature, but from this date we had used this type of machine, so the numbers are totally different that from this time on. So this is actually a big problem as well, because we need a data set that is completely cohesion, is very clean and ready to train. But yeah, the problem is...
So sorry, so in a perfect world, you have a model targeted on a very specific problem with near perfect data.
That's right.
Okay.
It never happens, but
Of
yeah.
course, but it's important to set the scene.
Yeah, exactly. So it's a lack of data that many companies are facing. So for that, we are creating a model that can create more data that we call synthetic data. So a synthetic data is basically a model, a trained model based on some sample of the data that we get from the companies or some other places like open source data anywhere, and which is trying to mimic the actual data. This can be actually working in different paths as well. Sometimes we want to just mimic the data and expand it to have more data to train the models on. Sometimes we want to see more extended data. So for it's like if we don't have the seasonality seen by the original data, so we want to see that as well. So we're gonna have some kind of more instances into the data as well. Sometimes we want to add rare data because that's essentially needed for a model to stop it from overfitting to data. So basically, we can generate data and use it to train the models.
So in the case of that that first starting point with HHA, we had a small amount of data. They'd had some, but there was a small amount of data available to us, but it wasn't enough for us to adequately train a micro model. Even though we'd gone small, focused, we still need a little bit more data. We needed 12 months history, let's say, because there was a seasonal component to it. And what you're saying is we've got technology built within Entropy that allows us to expand that 3 months worth of data to create another 9 months, so that we've now got a 12-month data set. And it does so in a way that is not copy and paste.
No.
It does so in a way where it actually learns the characteristics of the data and actually expands it materially. And this is using a technique, this is using another type of generative AI, isn't it? This is using something called GAN.
Yeah.
And you've actually, this is a core reason that you've been nominated for this Rising Star Award, because of the work that you've done with the University of Essex and Entropy helping with this. But I mean, Shaheen's introduced it really, really well, Waylin, but I wonder whether you could just expand a little bit further on exactly what's happening, exactly how we do this, because I know we use concepts of clustering and transfer learning and using reinforcement learning to identify feature importance. Well, that's the starting point, isn't it? But maybe you could explain a little bit further about what's going on here.
Let me take some simple words.
Yes.
I think that's easier. Like when we try to develop the synthetic data, we try to pinpoint if it is possible for us to generate the synthetic data based on the constraints. Like in that case, that we could have the different conditions, and then we generate the synthetic data based on the conditions that we want. And And after that, then we could have the total synthetic data to including more different situations, and then to put it and combine it with the real data that we got to train the one micro models. Because even for that micro models is we are lack of data. So if we just train the models based on the only real data, is lack of the situations that from the general environment. So with the constraints, and then to find out the patterns from the real data, and then to put some constraints on to make it possible to extend the whole data, and then to train them one micro models. Yeah. I don't know if I explained that.
No, that's well. There is a paper coming out.
It's hard to explain.
It's very, very hard to explain. I know, but the principle is that. I mean, the way I always explain it, the way it was explained to me, is you have two AIs or two neural networks effectively competing with one another. But what they're ultimately trying to do is one's trying to deceive the other, and the other's trying to detect real from fake. And in order for the deceiver to get better at producing, data that's easier to deceive the detector, it needs to learn the data set that it's mimicking. And the way that you teach the deceiver how what to mimic is you use a particular type of AI to effectively say these are the particular features that you want to mimic, and then it uses transfer learning from other data sets to essentially say, okay, well, this is how these features have worked in other data sets. So it starts to get better and better and better. Put enough compute power behind that, and you're away. Is that fair?
That's fair.
Yes.
Yeah. Very good. No, but it's a really important point. We can't make data from nothing.
Yeah.
But we can expand small data sets, and the micro models methodology is really, really important to that because of that focus that you were talking about at the start. And so we end up with models targeting very, very focused problems, very, very specific problems with near perfect data.
That's right.
So we've gone through why we need micro models. We've gone through the benefits of micro models. And just to remind everyone, very, very targeted, very focused models delivering very accurate predictions, chained together in a network that can be deployed iteratively, so we can learn as we go, we can take on different challenges as we go, that is sort of emboldened or made better through the use of synthetic data, ultimately enabling us to create these very, very powerful webs of intelligence across complicated operations. But the elephant in the room is this all sounds great, but surely that means you're going to have to build loads and loads and loads of models. Yes. Now, Waylin, you're working on something that we're calling generalization, but it goes directly to this problem, right?
Yep.
Maybe you could expand a little bit on that.
For example, right now when we are keep building the models, is like the models become more and more. If we just keep focus on building each models, it will spend longer time, because when the problem's getting bigger, then it will need to split to the more small problems, and then you need to build more models. And then in that case, we come up with the idea is what if we could generalize the process of building the micro models, and if we could do that, that will be better, shorten the times of the models, and then easier, faster to show the clients about the outcome for all the models. And during that time, we are get in touch with the different cases.
Yeah.
So every time we get to new cases, we build the process of based on that cases. In that way, when the similar cases coming in, that we could just make that case because it's a similar case, so we could make the process general better to the similar case, and then it will shorten the time when the similar cases come.
So again, learning from what we've done.
Yeah.
So the more we deploy, the quicker we get at deploying micro models.
Yes.
Is that fair?
Exactly.
Yeah. Is there anything you'd like to add to that particular part?
We at first said that even the same concept that you have about the models, each of these micro models, you might have completely different behavior. This is actually quite opposite, that it can contradict it, but it's not like that.
We love a good contradiction.
Yeah. It's like many times in different situations, you will see the similar features and similar characteristics in the data. So it's not like we copy paste a model to see it, it's like to see that which model we can copy paste for this new situation that we're in. It's try to understand that, all right, this is the feature that we had before. What we did in the before can help us in the model as well. So it can help and speed up the process of model creation.
Yeah, and the system that's being built around it, again, is using lots of different types of AI to help identify and orchestrate certain aspects. So really, really quite powerful. Guys, thank you very much. I think one area, just to kind of a bit of a fanfare to finish on, would be just to sort of say that this is not a new concept for NTP now. We deployed our first micromodel in 2022. We average an accuracy north of 92-93% on each one of the models. We are predicting traffic to the port of Dover. We predicted to north of 95-96%. In complex port operations, we're predicting things like pilotage movement duration, so how long a vessel takes from the moment the pilot boards the vessel to the moment it's alongside at berth or fast. We're predicting that within minutes sometimes. The flow of passengers through airports. There's an article out, it's open press, but the AD plant provider that we worked with couldn't believe that within 5 weeks we were able to predict biogas yields to north of 85% accuracy, and we moved that above 90% very, very quickly afterwards. So this concept works. We have been able to deploy predictive intelligence in the harshest environments. And I really appreciate you both taking the time to come and help explain some of the clever bits behind it. So with that, thank you. And thank you all very much for listening. See you soon.